So imagine you are standing on a perfectly swept factory floor and you're just, looking at an absolute marvel of modern engineering.
Oh, it's a great feeling.
Right. You have just signed the purchase order for this top-tier CNC lathe. It's gleaming, it is high-tech, and it represents a really massive financial commitment for your production line.
Definitely a big day.
Exactly. You are ready to start turning raw metal into these highly precise components, and you're fully expecting this incredible piece of technology to just completely transform your daily operations. But according to the manufacturing specifications we're reviewing today for this deep dive, there is a hidden, incredibly expensive trap waiting for you.
Yeah. And it is a trap that catches even the most seasoned manufacturing planners completely off guard.
Really?
Oh, absolutely. And I mean, the most frustrating part is that this mistake happens long before the first piece of metal is ever even cut on that floor.
Wow. Well, we are looking at some really fascinating technical manuals today that reveal this massive blind spot in factory planning. Because here's the surprising hook, and this blew my mind a bit. You can buy $1 million machining center, but that entire machine is fundamentally useless if your work holding system, like the chuck, the actual jaws that grab the part, is specified incorrectly.
It's essentially a very expensive paperweight at that point.
Exactly. So our goal today, our mission for this deep dive, is to unpack why choosing the right chuck during that initial planning phase is the actual secret to maximizing your return on investment and ensuring your production doesn't just grind to a halt.
Because diagnosing a work-holding issue after production has already begun
Yeah,
is just an absolute nightmare for any facility.
I can only imagine.
Yeah, it's terrible. The core mission is to align your underlying technology with your daily operational goals right during the initial equipment specification. You never want to find yourself trying to fix a foundational hardware mistake while the machines are actually supposed to be running a live batch of parts.
Okay, let's unpack this. Because we are looking at a core, really historical debate in the manufacturing world. The hydraulic chuck versus the pneumatic chuck. Right.
Heavyweights.
And before we can even begin to talk about how fast a machine can make a part, we really have to talk about the brutal physics of holding that part perfectly still against some incredibly violent cutting forces.
Yeah, and the physics of the fluids involved are really what drive this entire decision. We are talking about two fundamentally different physical principles here.
Right.
A hydraulic chuck uses pressurized fluid, specifically like a thick, heavy hydraulic oil, to provide the clamping force.
Okay.
And you have a dedicated pump that pushes this oil to massive pressures. We're talking 3.5 MPa or higher.
That is a lot of pressure.
It is. And the defining characteristic of this thick oil, the thing that changes absolutely everything about how the machine behaves, is that it is fundamentally incompressible.
Incompressible. Okay, so to put that 3.5 MPa into perspective for you, the listener, we have to look at the other side of the aisle. The pneumatic chuck system uses compressed air. Usually this is just the regular shop air piped through your factory.
Right, exactly, just the standard airline.
Right, to clamp down on the metal. And that shop air operates at a much lower pressure, specifically between zero point 0.4 to zero point 0.6 MPa.
A huge drop-off.
Right out of the gate. The hydraulic oil is operating at nearly 10 times the pressure of the pneumatic air. But it isn't just about the raw pressure number, is it? It's really about how those fluids behave under stress.
Yeah, that behavior is the true differentiator. Unlike that thick hydraulic oil, air compresses very easily.
Yeah.
Think of it on a molecular level. In hydraulic oil, the molecules are already packed incredibly tight. There is simply nowhere for them to go.
Right, they're jammed in there.
Exactly. But with compressed shop air, there's still empty space between the gas molecules. So when a force is applied to that gas, that empty space basically allows the molecules to compress even further.
I want to make sure you can really visualize what this means when a cutting tool slams into a piece of metal. Think about the hydraulic grip, like clamping down on a solid block of concrete.
It's a good way to put it.
Right. Once those jaws close, there is just nowhere for the oil to go. It is an immovable, completely solid wall of force.
Yep.
But the pneumatic grip, because of that empty molecular space in the gas, is much more like squeezing a tightly inflated rubber tire. You can squeeze that tire really hard, but because there's air inside, there is always going to be a little bit of squish when you apply sudden pressure.
Yeah, that squish effect perfectly describes the vulnerability of a compressible gas under a dynamic cutting load. The system just inherently has some give to it.
Wait, I'm trying to wrap my head around this. If the pneumatic system is just using shop air, why don't we just engineer a stronger air pump?
I see where you're going.
Yeah, like why not just crank up the air pressure, force those molecules together, and make it just as strong as the thick hydraulic oil?
It raises an important question, but the engineering data from our source text completely shuts that idea down.
Oh, really?
Yeah, the physics simply do not scale that way. The text is very clear on this. Even if you invest in a top-of-the-line, super high-performance pneumatic chuck, it absolutely maxes out at 59 kilonewton of force.
But 59 kilonewtons sounds like a massive amount of force on its own. Why isn't that sufficient to hold a standard heavy part?
Because the cutting forces generated when you're machining tough alloys are incredibly violent.
Oh, okay.
It just cannot match the unyielding grip of incompressible oil. It's actually physically impossible for that compressible gas, even at its absolute maximum engineered limit, to provide the same stable clamping force as a high-pressure hydraulic system.
That makes sense.
And because of this physical limitation, engineers have actually established a strict golden rule when specifying air chucks. You need the air grip to be exactly 1.3 times the weight of your part.
Wait, 1.3 times? That is a very specific safety margin you have to hit.
Very specific.
So if your part weighs a certain amount, your grip basically has to exceed it by 30% just to compensate for the fact that air compresses.
Exactly. Which means that metric entirely dictates the application.
How so?
Well, because you are bound by that 1.3 times weight limit, you must use pneumatic chucks strictly for lighter materials, things like light aluminum and plastics.
Ah, I see.
Yeah, if you attempt to load heavy mold steel or large aerospace shafts, you will just exceed the capabilities of the air. You must use the hydraulic system for those applications, relying on that massive clamping force to handle heavy cuts on tough, dense alloys.
Okay, well, here's where it gets really interesting. Because if hydraulic oil gives you that ultimate immovable grip and it handles heavy metal so flawlessly, I have to wonder why a factory planner would ever choose the weaker pneumatic air system.
Right. It seems counterintuitive at first.
Yeah. Why not just use the strongest, most secure grip every single time and not worry about the weight limits at all?
And that brings us directly to the economics of high-volume manufacturing. When you move away from requiring raw, heavy power, your priorities shift entirely toward automated speed and overall equipment effectiveness.
It's a different ballgame.
Completely. The goal becomes minimizing cycle times.
Let's actually break down the math on this because this is where fractions of a second completely change the financial game for a factory.
They really do.
We are talking about jaw movement time, like the literal time it takes for the chuck to open up, drop a finished part, and close on a new piece of raw metal.
Exactly.
According to the manual, a pneumatic chuck using that lightweight compressed air opens and closes in just 0.3 seconds.
It is practically instantaneous.
Now compare that to the hydraulic chuck. Remember that thick, heavy hydraulic oil we talked about? Because it is so dense, it moves slowly through the internal pipes and valves of the machine. The hydraulic system needs 0.5 to 1.70 full seconds just to move the jaws.
And, half a second might sound like an incredibly tiny difference to a layman.
But let's look at the reality for you on the factory floor. Let's do the math. Say your facility is running an automated line making 10,000 parts a day.
A very realistic number.
Right. If you are saving half a second on every single part you load and unload, that is 5,000 seconds saved.
That's huge.
It is nearly an hour and a half of pure, uninterrupted production time you are getting back every single day just by using air instead of oil. Over a year, those fractions of a second compound into entire weeks of free manufacturing time.
Yeah, in high-volume manufacturing, those seconds translate directly into massive annual financial gains. You are increasing your yield without adding a single new machine or hiring another operator.
And beyond just the speed of the jaws, the choice of an air chuck actually changes the entire physical layout of your factory, doesn't it?
It does. It simplifies the floor plan immensely.
Really?
Oh, yeah. By utilizing a pneumatic chuck, you are running off the existing shop air infrastructure. That completely eliminates the need to purchase and install a dedicated hydraulic power unit for the lathe.
Which frees up a lot of space.
Exactly. You remove complex oil pumps from the equation, and you don't have messy, highly pressurized oil hoses running across the floor or inside the machine envelope.
So you are left with a vastly cleaner setup.
It provides a perfectly clean operation, and that cleanliness is absolutely mandatory if you are running medical device factories or food processing facilities.
Right, because a leak would be disastrous.
Yeah, a hazardous fluid leak would compromise an entire sterile batch. Furthermore, this clean, streamlined design pairs seamlessly with robotic loading arms. The text actually notes that this automatic centering structure grabs the part instantly, which reduces your overall job setup time by an astonishing 20 to 60%.
Wait, a 60% reduction in setup time is wild.
It's massive.
So if your business model is running huge batches of, say, small car parts or light aluminum widgets, the pneumatic system is giving you an incredibly fast, highly automated, and perfectly clean production line.
Yep, it delivers extreme speed and significantly lower operating costs day in and day out for those very specific lightweight applications.
Okay, so pneumatic speed is clearly amazing for high-volume, small car parts. But what happens when you are manufacturing parts that require strict life-or-death tolerances?
That changes everything.
I mean, if we are talking about aerospace components for jet engines or medical implants that literally go into the human body, there is zero room for error.
What's fascinating here is how the elemental physical properties of the fluids we discussed earlier completely dictate the level of precision you can practically achieve.
We're back to the fluids.
Always back to the fluids. When you are machining strict tolerance aerospace or medical components, you must maintain absolute stability under pressure.
Right.
Microvibrations or the slightest shift under a cutting load will instantly ruin the part and destroy your yield.
Which means the hydraulic system has to step back into the spotlight.
It wins the precision test without question. And it all traces back to that incompressible thick oil.
Because it doesn't give.
Exactly. Because the oil cannot be compressed, the dedicated hydraulic pump maintains the exact same continuous pressure all day long. When you load a piece of titanium or heavy steel, the jaws clamp down and provide a completely unyielding grip.
Going back to that solid block of concrete analogy, there is simply no empty molecular space for the system to compress into.
And that solid grip provides excellent vibration damping.
Damping the chatter, right?
Yeah. When a carbide cutting tool hits a spinning piece of steel, it creates violent chattering and vibration. The hydraulic oil absorbs that energy. The constant high pressure stops the part from pushing away from the tool.
That makes total sense.
This superior vibration damping greatly improves your surface finish on the metal, and it actually extends the life of your really expensive cutting tools.
And run out, meaning the part isn't going to wobble off its true center as it spins, is kept completely in check.
Yes, the hydraulic chuck gives you ultimate control over that runout. Because of this extreme rigid stability, you can achieve a repeat positioning accuracy of under 0.01 millimeters.
Under 0.01 millimeters. Okay, to give you, the listener, a sense of scale, a standard human hair is about 0.07 millimeters thick.
So we're talking incredibly tiny.
Yeah, we are talking about the machine opening its jaws, grabbing a completely new piece of metal, and hitting a repeatable center point that is a tiny fraction of the width of a single human hair every single time, all day long.
The repeatability is staggering, but it requires the constant, unwavering pressure that only an incompressible fluid can provide.
I am still curious about the pneumatic system, though. If it is so high-tech and it pairs so beautifully with advanced robotic loading arms, why exactly does it struggle to hit that fraction of a hair precision? Like, what is happening inside the air system that ruins that tight tolerance?
The vulnerability lies in how shock air actually functions in a real-world factory environment. Your factory's air pressure is not a constant, isolated force.
Oh, because it's shared.
Right. Shop air isn't a dedicated line just for your lathe. Throughout the day, someone across the factory floor hooks up a blowgun or a massive pneumatic press kicks on, and suddenly the pressure in your shared air line drops. It fluctuates constantly.
So your clamping force is at the mercy of whatever else is happening in the building.
Exactly. And when the cutting tool hits the part, creating a heavy dynamic load, remember that the air compresses easily. The part actually pushes back against the jaws.
Oh, wow.
Yeah, because the air behind those jaws compresses into that empty molecular space, the jaws physically move a tiny bit.
They squish?
They squish. And that minute movement, that tiny shift backward under load, completely ruins your tight tolerance.
That is wild.
This is exactly why you must use oil power for strict tolerances. The pneumatic system simply cannot guarantee the long-term positional repeatability required when a fraction of a millimeter means the difference between a functional aerospace part and just expensive scrap metal.
So what does this all mean? We have established that hydraulic oil gives you this immovable, flawless precision, while pneumatic air gives you blazing speed. But maintaining either system under these extreme factory conditions day in and day out must take a severe toll on the hardware itself.
Oh, absolutely.
You don't just buy a chuck on day one and forget about it. What happens when these systems inevitably wear down?
A chuck's true cost extends far beyond the initial purchase price. It includes long-term maintenance, labor hours, and the ever-present threat of unexpected downtime.
Right.
Understanding the specific environmental demands of each system is the only way your maintenance team can implement effective preventive care. As the source text bluntly puts it, bad maintenance destroys good machines.
Looking at the manual's maintenance schedule for the pneumatic chuck, I have to say it sounds incredibly needy.
It is a bit demanding.
It requires a tremendous amount of daily, hands-on attention from your maintenance crew.
It demands strict daily care, but it is a very specific mechanical type of care to counteract the friction of that extreme speed.
Yeah, the text is very explicit about this. For the pneumatic chuck, you have to manually pump molybdenum disulfide grease into the system every single day.
Yep.
And you don't just give it a little squirt. You have to pump that thick grease until it literally pushes out of the front face of the chuck.
You have to guarantee the internal sliding mechanisms are completely lubricated. If you skip that grease, friction builds up, and you immediately lose that 0.3-second automated speed that justified buying the pneumatic system in the first place.
And on top of pumping the molybdenum disulfide grease daily, your team has to constantly monitor the air filters. You have to drain the moisture from the shop air lines.
Oh, moisture is the enemy.
Right. If you don't keep that incoming air perfectly dry, the moisture will accumulate inside and destroy the rubber seals.
If we connect this to the bigger picture, the pneumatic chuck is high maintenance, yes. It requires daily greasing and perfectly clean, dry air. But it offers one massive factory-saving advantage.
Which is?
It never leaks oil.
Ah. Which makes sense because there's no hydraulic fluid in the system to leak in the first place.
Exactly. And that completely eliminates the need for a hazardous materials cleanup on your floor. But with the hydraulic system, you are living with a much more systemic maintenance reality and, frankly, a constant threat of catastrophic failure.
That sounds stressful.
It is. You have a dedicated hydraulic power unit that takes up floor space. You must keep environmental dirt out of that reservoir. You have to service the oil pump, replace the thick fluid filters regularly, and crucially, you have to monitor the oil temperature constantly.
Temperature seems to be the absolute killer for hydraulic systems.
It is the primary failure point. If that thick hydraulic oil gets too hot specifically, if it rises over 50 degrees Celsius, that thermal energy completely ruins the internal rubber seals.
And let me paint a picture of what happens when a hydraulic seal breaks under 3.5 MPa of pressure. You get a massive, catastrophic failure. Broken seals mean gallons of thick, hot oil spraying and leaking all over your pristine factory floor.
It's a nightmare.
It is a hazardous, messy fluid leak that forces you to halt production immediately, quarantine the area, and spend hours on cleanup and repair.
You are essentially trading the daily, needy greasing schedule of the pneumatic system for the looming threat of a catastrophic, messy oil leak with the hydraulic system if that fluid ever crosses the 50 degrees Celsius mark.
That is a stressful trade-off.
It is. However, the pneumatic system does feature a brilliant built-in safety advantage.
Oh, what is that?
Well, the air chuck has a simpler inside structure, and it incorporates a mechanical safe lock. Even if an errant robotic arm completely severs your shop air hose and you lose all air pressure instantly, that safe lock engages and holds the spinning part securely so it doesn't become a lethal projectile.
That is incredible peace of mind when you have heavy automation swinging around the machine. Now, despite these differences, there is one crucial maintenance reality that both of these systems share, regardless of whether they use compressible air or incompressible oil.
The deep cleaning schedule is universal. Both the hydraulic and the pneumatic chucks require your maintenance team to perform a full teardown and a deep cleaning every 6 months to keep operations running at peak efficiency.
But there is a massive exception to that 6-month rule, and it entirely depends on what kind of raw material you are cutting in the machine.
Yeah, the environmental demands of the material can drastically accelerate that maintenance timeline.
The text actually singles out cast iron. Think about standard aluminum or steel. When you cut it, it usually forms these long, continuous curls or clean chips.
Right, manageable chips.
But cast iron is brittle. When the cutting tool hits it, the material shatters into this microscopic, highly abrasive dust. It acts exactly like fine sand.
It gets everywhere.
If that abrasive dust works its way into the chuck, it grinds against the internal gears and sliding surfaces.
Right.
Because it is so destructive, if you are cutting cast iron, you cannot wait 6 months. You must tear down and deep clean both types of chucks every 2 months.
And every 2 months is a grueling, labor-intensive maintenance schedule.
A bit.
But it is mandatory. If you let that abrasive iron dust sit inside the mechanisms, it will permanently destroy the accuracy of your $1 million machine.
All right, let's bring this all together for you, the listener. If you are planning out your factory floor and you want to maximize your return on investment from the very first day, here is how you align the technology with your exact daily work. You choose the hydraulic chuck if you are making heavy cuts on tough alloys, like dense mold steel or large aerospace shafts.
Definitely.
You choose it when you need absolute precision and repeat positioning accuracy under zero point zero 0.01 millimeters, relying on that dense, incompressible oil to provide a solid grip and excellent vibration damping.
Conversely, you specify the pneumatic chuck when your primary operational goal is high-volume efficiency. If you are manufacturing tens of thousands of light aluminum or plastic components and you need that blindingly fast 0.3-second jaw movement to shave hours off your cycle times,
Yeah.
you choose pneumatic when you are fully integrating robotic loading arms, aiming for perfectly clean operations in medical or food processing facilities, and you have a maintenance team willing to manage the daily molybdenum disulfide greasing to keep that speed alive.
So it all really boils down to matching the specific physical capabilities of the chuck to the specific weight, the daily volume, and the precise tolerance of the part you are manufacturing. It is a foundational choice.
It is, and if I can leave you with one final thought based on the highly technical texts we have reviewed today.
Please do.
It is truly wild to step back and consider the incredible scale of modern industry. We are talking about multi-million-dollar, ultra-precise, fully automated manufacturing facilities. Facilities that produce the flawless aerospace shafts that keep commercial planes in the sky, or the microscopic medical devices that save lives in hospitals.
It's amazing stuff.
It is. And yet the ultimate success of all that towering high-tech engineering hinges entirely on the most basic, elemental principles of fluid dynamics.
The fundamental behavior of fluids under pressure.
Precisely. The absolute perfection of a strict tolerance aerospace component is entirely at the mercy of whether the thick oil in a hidden pump happens to get a little too hot, breaching that 50 degrees Celsius mark and melting a simple rubber seal, or whether a tiny bit too much moisture builds up inside a cheap shop air hose.
That's a crazy perspective.
We build these massive monuments to precision engineering, but at the end of the day, our most advanced technologies are still completely bound by the unyielding laws of physics and the raw nature of the fluids that power them.